Hi, my name is Peng Shi, and I'm an assistant professor at the University of Southern California. My research focus is optimization in matching markets. One question that has puzzled me is why is it that matchmaking seems so much easier in certain industries versus others? For example, Uber, Lyft, and Airbnb have transformed the ride-hailing and accommodation industries, whereas similar platforms have really struggled in the home services space. The paper I'm presenting to you today addresses this question using a rigorous model based on information theory. The title of this talk is Efficient Matchmaking in Assignment Games with Application to Online Platforms. The online platforms I'm referring to are those that match the right customer to the right service provider at the right price. I'll be analyzing these platforms using the assignment game model of Shapley and Schubrick 1971, which is a standard model of two-sided matching with monetary transfers. The novelty here is to use information theory to rigorously quantify the efficiency of any given system of forming matches. Let me motivate this paper by summarizing the shortcomings of previous research on improving the efficiency of matching platforms. By efficiency, I mean to minimize the time and effort agents need to expend in order to find a suitable match. There are three approaches of previous research. The first is a field experiment, which is useful for quantifying the impact of a given policy change. However, such an approach cannot quantify the potential for further improvements. A second approach is search theory, which is to analyze the equilibrium behavior of agents under a given platform design. However, such an approach requires strong assumptions on how exactly agents behave and interact on the platform. The third approach is communication complexity theory, in which one defines a notion of a good market outcome and asks, what is the minimum number of bits of information that need to be communicated in order to arrive at this outcome? Under such an approach, efficient matchmaking means to come up with a good outcome with low amount of communication. Previous papers on this approach, however, do not allow endogenous prices, and they suggest that low communication costs, which means having the number of bits of communication per agent being polylogarithmic in the market size, is not possible in typical markets, which is a discouraging finding. This paper overcomes all of the shortcomings in red. In particular, I adopt the communication complexity approach but modify the notion of what is a good outcome. And doing so, I'm able to quantify the potential for further improvements with low amounts of assumptions on what agents can do and what the platform can do. As well, I do allow for endogenous prices and show that very low logarithmic communication cost is indeed possible in a wide variety of markets. Here's a summary of insights in table format. The first column corresponds to the individual contributions of this work. The first contribution is to analyze two-sided markets with endogenous prices using communication complexity theory. The second contribution is to define easy and hard to match markets based on the distribution of preferences. The third contribution is to quantify the minimum number of bits of communication per agent needed to reach a good market outcome. The fourth contribution is to derive near optimal matchmaking protocols. So which markets are easy to match? I showed that there are ones in which the horizontal preference of one side is easy to satisfy. For example, in ride-hailing or routine home services, customers don't really care which provider they're getting, as long as they provide a certain level of acceptable service. A similar statement can be made for Airbnb hosts. However, hard-to-match markets are those in which the horizontal preferences of both sides are hard to satisfy. For example, when parents are finding nannies, both sides may be particular about what kind of a match they're looking for. A similar statement can be made for non-standard home improvement projects. For easy-to-match markets, the minimum number of bits of communication per agent grows as logarithmic to the market size. Whereas for hard-to-match markets, it's between square root of n and square root of n log n, where n is the number of agents. For easy-to-match markets, I show that near-optimal protocols can be as simple as having a searchable directory of the easy-to-satisfy side. For example, for Airbnb, since hosts are relatively easy to satisfy, we have a searchable directory of listings. And if both sides are easy to satisfy, the platform can simply recommend a few feasible matches, similar to as in Amazon Home Services. However, in hard-to-match markets, near-optimal protocols need to allow both sides to initiate contact while limiting the total number of contacts. The next two slides outline the model in which these insights are rigorously shown. The model is based on the assignment game of Shapley and Shubik 1971, in which there's a set of customers, a set of providers, and each agent is looking to be matched with at most one partner. The surplus of a match between customer I and provider J depends on the benefit received by the customer minus the cost of service, where the benefits and costs may depend on the IJ pair. For each match, customer and provider divide the surplus as follows. The customer pays PI to the provider, and so the customer's surplus is UI, which is the benefit minus the price paid, and the provider's surplus VJ, which is the price received minus the cost of service. So far, everything here is in Shapley and Shubik. What's new in this paper is the incomplete information, in which I assume only customer I knows the benefit BIJ, whereas only provider J knows the CIJ. So finding a good match requires communication. Moreover, the matrices B and C are jointly distributed according to a preference distribution F, which is commonly known. You can interpret F as the platform's belief on agent preferences after conditioning on initial information collected when agents sign up for the platform. Hence, a market is formally represented by a set I of customers, a set J of providers, and a preference distribution F. For a given market, I quantify the difficulty of matchmaking via the delta area communication complexity of epsilon stable outcome. This definition requires two parameters, delta and epsilon. The formal definition of this is the minimum number of bits of communication per agent needed to achieve a good outcome with high probability, where the notion of a good outcome is this notion of epsilon stability. Here, there's a matching X and a payment vector P, which induce division of surplus U and V. These customer and provider surpluses need to satisfy the following two equations. The first equation, no epsilon blocking pair, states that any pair of customer and provider who are currently not matched will not get more than epsilon from matching on their own outside of the platform. The left-hand side, UI plus VJ, is what they currently have, and after giving them epsilon each, this has to be greater or equal to what they will get on their own, which is Bij minus Cij. The second condition, individual rationality, says that the surpluses must be non-negative, so everyone is willing to participate at a given match and payments. Without loss of generality, I normalize the support of the benefit and costs to be between 0 and 1, so as to give a scale for epsilon. When epsilon is 0, this is exactly the classical notion of a stable outcome in an assignment game. And the modeling innovation in this paper is to introduce this epsilon, which helps us to bypass certain impossibility results encountered in previous work. Having outlined the model, I'll move on to the results. I'll begin by elaborating on the definition of easy and hard to match markets by giving formal statements of what I mean by these. A market is easy to match if the horizontal preference of one side is easy to satisfy. To make this precise, I have to define what I mean by horizontal preference as well as easy to satisfy. Let's pick one side of the market, say the providers. We can always decompose the cost as the sum of certain vertical terms that are common across providers and customers, and the residual I define to be the horizontal preference. Easy to satisfy with parameters epsilon and d means that this horizontal preference gamma ij is close to this lower support underbar gamma ij with at least a constant probability. Moreover, there are certain independence assumptions on the gammas as well as common knowledge assumptions on their distributions. What this means is that although the cost of a provider for a given customer may be uncertain and there may be substantial variation, the best deals that a provider can offer is open to a constant proportion of the market. In other words, the provider is not so picky about whom they can serve cheaply. Under this assumption, the delta area communication complexity of epsilon stable outcome scales as the logarithm of the market size n, where n is the total number of agents. The constant may depend on delta, epsilon, and d. This is the best one can hope for, since even giving every agent a unique ID and communicating the identity of one agent requires logarithmic bits of communication. On the other hand, a market is hard to match if the horizontal preferences of both sides are hard to satisfy. Let me illustrate with an example. Suppose that the benefits and costs are IID drawn from these distributions, in which the benefit is high with a small probability of 1 over square root of m. And similarly, the cost is low with a very small probability. The theorem states that the delta area communication complexity for this market is at least a constant times square root of n. To give some intuition, note that in this market, in expectation, each agent has only one profitable partner for whom Bij is high but Cij is low. But in order to find such a profitable match with high benefit and low cost, each agent needs to ask square root m partners before finding someone who reciprocates interest. In the remaining time, I'll briefly overview the near-optimal matchmaking protocols. Here's an asymptotically optimal protocol for easy markets. There are two phases. In the first phase, the platform computes initial cost estimates Eij based on commonly known information as well as cost information for a few pairs of agents. These initial estimates Eij are optimistic, meaning that they're guaranteed to lower bound the actual costs. In the second phase, customers reach out to providers in decreasing order of estimated surplus, which is the benefit minus the cost estimate minus a price premium charged by each provider. These price premiums are initialized to 0, and as providers receive more requests, they increment the price premiums based on demand. Moreover, as customers reach out to providers, they find out about the actual cost Cij, and they increment the cost estimate based on provider feedback. This process terminates if every customer has found a provider whom they can serve at the estimated cost, or they found out that they do not have non-negative estimated surplus with anyone. The theorem is that for easy-to-match markets, the above computes an epsilon stable outcome with high probability using logarithmic bits of communication per agent. For hard markets, the protocol needs to be modified to allow providers also to initiate contact. There are now 3 phases. The first phase is analogous to before, in which the platform computes these initial cost estimates. However, these need to be based on a more complex formula that is based on the CDF of the horizontal terms gamma ij. The second phase, which is conceptually new, is where providers reach out to customers for whom the cost estimate is too high, and the customers will update the cost estimate to be the real cost in this case. You can think of this as providers reaching out with special deals to select customers. The third phase is identical to before, and customers reach out to providers in decreasing order of their estimated surplus, with providers updating their price premiums and customers updating their cost estimates along the way. The theorem is that for any market, the above computes an epsilon stable outcome with high probability. The number of bits of communication per agent is at most square root n log n whenever the gamma ij's are independently distributed. This is close to the square root n lower bound, and the condition is relatively weak since the gamma ij's can be based on different distributions for each ij pair, and there are no additional assumptions on the distributions. This is really saying that the correlations in costs are entirely captured by the vertical terms alpha I and beta j. Moreover, whenever the market is easy to match, this protocol achieves the optimal rate of logarithmic communication per agent. This is because these initial cost estimates for easy markets are guaranteed to lower bound the actual costs. So nothing happens in step 2 here, and this protocol is essentially the same as the previous protocol for easy markets. Here is the summary of insights again. Since this is ongoing work, I'll very much welcome if you have any feedback. Feel free to reach out to me at the email address above.